This is just a short video on projectile motion. Obviously this pertains to the second phase of the long jump in your example that you've got for your assessment for this module. So a word of warning before we begin: if you are not confident with trigonometry, I would advise you to go back and revise that before progressing onto this video. Likewise, you may have come across a rather scary number of equations. If you've already been doing some reading on projectile motion, I would very much encourage you to stick to only the equations that we use in this specific video, because if you want to keep your sanity anyway. So let's begin. What then is a projectile? Well, a projectile can be anything that is launched into the air. It could be something that you perhaps kick, like a ball, or it could be a shot that is put in the shot putting example here. It could be something that's free falling, perhaps a diver, or a long jumper, say, which is particularly pertinent to us in this situation, obviously. But it's any object that is launched into the air and is now only subject to the laws of gravity acting upon it. It is a projectile that is just flying through the air. Now, one way that I think of this, don't quite know why, but is in the context of a video game. I have a friend who works in games design, and sorry, I have a very creaky chair at home. I have a friend that works in games design, and we were chatting the other day, and he said that you have to create in-game physics for a computer game. And I never thought of this before, because I was a huge fan of Sonic the Hedgehog growing up, and I do like my physics. And you obviously have to create gravity in the green hill zone here. Otherwise, when you jump to try and clear these spikes, Sonic would float off Mobius, and that would be devastating because Robotnik would win, and we won't have that. So I'm going to fulfill a boyhood dream here, because here comes Aaron the, not hedgehog, but stick figure. There he is. Now, in the game, for any of you that have played it, you will perhaps remember that once you jump into the air, you can still control the direction of movement of your character. Now, you can't do that in real life. Once you jump, if you're running forward and you jump to the right, you can't then suddenly turn left because you've changed your mind when you're mid-air. You're just going to keep going left. There's not much you can do about it. But that's not the same as in the game. Now, if we were to plot the area that I covered when I jumped here, when I was clearing this first set of spikes, and not so successfully on the second set, but you would see that I created this curved shape as I jumped through the air. And you can break any point of this down into its horizontal and vertical components. You could do the same for the second jump here. So if you were to consider my peak jump height represented by these two red crosses, you could figure out how far I jumped vertically and horizontally. And that's essentially what we're going to be doing for our projectile motion equations. Let's look at a slightly silly example. This is just a simple series of photographs that have been laid over each other to show the path of travel, the displacement of a ball that's thrown into the air. You can do this yourself if you want. If you have a smartphone with a slow motion video recorder, you can throw anything into the air and it will always produce this shape, this bell-shaped curve, which we call a parabolic curve. And I'll explain why that is in a moment. But essentially you will always get this same shape. Now, when we jump into the air, we have two primary factors that limit how far we will jump up or to the side. The first of those is going to be wind resistance, which I've tried to represent here with a fan. But in most situations, wind resistance is negligible. It's insignificant. You very seldom will see a long jumper jumping when there's a hurricane nearby or gale force winds. And so the effects of the air, of air resistance, when there is little wind around, is negligible. The air doesn't stop us from moving, really. So we forget about it. We don't worry about it for the sake of our equations anyway. The only thing we're concerned about is the effects of gravity, which we represent here as the body weight. For any of you that have ever shown an interest in astronomy or have interested in sort of space travel or anything like that, you may have heard astronauts refer to an object as being weightless. So when they're, I don't know, orbiting Earth in space shuttle and they're carrying something around and it's floating around in the shuttle, they'll say, oh, it's weightless. And that's a very specific use of the terminology because the object still has mass. It's not lost its mass, but of course they're so far away from Earth that the effects of gravity are lessened. That's why it's floating around. So the object doesn't have any weight anymore, but it does have mass. Because we're jumping near Earth, we are very much subject to the laws of gravity, and they will pull us back down towards the Earth. So we have to overcome gravity, and that's the only thing that we factor into our equation, the only external force. We don't worry about wind resistance. So let's break these calculations that we're going to do down into three separate parts. The end product, the result, what we want to get to is to figure out how far you or your athlete jumped. That's what we want to find out. That's the purpose of doing these equations. You first need to work out the time that they were in the air. This is their jump time. And you also need to know their vertical velocity, specifically the change in average vertical velocity. So to do this thing, we need to introduce some new equations. New, but hopefully not too unfamiliar. This is the first. It looks scary, but it isn't. Remember, the triangle sign here is the Greek letter delta, and that is simply an abbreviation for change, or change in. So change in and whatever is to the right of the symbol. The dash, the little hyphen above the V on the left there in red, is an abbreviation for the word average. So this equation reads change in average vertical velocity. I should say the subscript y there, so y referring to the y-axis on a graph, so y up and down on a graph, x across a graph. So if it's up and down, then y represents vertical. So the equation reads change in average vertical velocity is equal to the final vertical velocity minus the initial vertical velocity. So you just take one number and take away another. It's relatively straightforward. Our second equation is delta t equals delta v y divided by ay. And this reads change in time, that's in blue, equals the change in average vertical velocity divided by the vertical acceleration. So the answer to the first equation that you do, the change in average vertical velocity, you simply divide that by the vertical acceleration and you will get delta t, the flight time. Now the vertical acceleration refers to the acceleration of gravity, which we know is minus 9.81. So whatever answer you get for the first equation, you just divide it by minus 9.81 and you'll get the flight time. So it looks scary, but it's not too bad. Our final equation is this one. Now, if you had to guess what S with the subscript X and the arrow above is, have a moment, have a think. What do you reckon it is? What do you think? Would you believe that it is horizontal jump distance? Why not have JD? Why not have H for horizontal? The arrow represents the that it refers to distance, as does the S. For some reason, S refers to jumping distance. No idea why. I wouldn't have chosen it, but there we are. But this equation reads horizontal jump distance, so how far the person jumped, is equal to the horizontal velocity multiplied by the jump time, delta t, change in time. And that's what we want to work out, the jump distance. So let's work through these one at a time. We first need to understand where this delta what Vy is coming from, the change in vertical velocity. How do we work that out? Well, here is Dr. Devereaux, and thanks to his previous years of resistance training and his colossally powerful lower limb extensors, he is going to perform quite the impressive vertical jump. Here's our equation. We'll pop that there just to remind us. Now let's pretend that his initial vertical velocity was 8 meters per second. And if you hadn't guessed already, this example is very much make-believe. I can't imagine he can jump 15 meters in the air. Now, let's pretend that after 1 second of jumping upwards, so he's left the ground, and after a second, he has now got a vertical velocity of 4 meters per second. So he's slowed down from his initial takeoff velocity, which was 8 meters per second. But then that makes sense because gravity's pulling him down. 2 seconds after having left the ground, he has a vertical velocity of 2 meters per second. And finally, he reaches his peak jump height, where for the briefest of seconds, milliseconds, he has a vertical velocity of 0. Very short period of time. He's now going to begin the descent. After 1 second of falling back to the ground, his vertical velocity will now be minus 2 meters per second. After 2 seconds into the descent, have a little guess, maybe pause, think about it, his vertical velocity will be minus 4 meters per second. I'm sure you can see a pattern emerging here. So considering that his vertical velocity at takeoff was 8 meters per second, what do we think his vertical velocity will be at contact? Minus 8 meters per second. Why? Because there's no other force acting on him apart from gravity. As long as he lands on the same level that he took off at, he's not jumping up onto something or down onto something, then his vertical velocity at impact is going to be the same as his vertical velocity at takeoff. It will just have a minus sign in front of it because he was falling down. So we now can use this information. We have the initial vertical velocity, we have the final vertical velocity, we can work out the change in vertical velocity. So have a go at that now using the numbers that we have here. Just pause this video. And you should have minus 16 meters per second. I hope that makes sense. This, of course, wouldn't be true if he was to jump down onto something, let's say, just for example. So let's say we took away the floor and he landed lower than what he was on when he previously started. There are ways of working this out, what his velocity would be at impact in this situation, but we will save that for another day. You can see, though, he has covered a greater distance, but again, we'll save that for another day. Your long jumper will be taking off and landing on the same level of ground. They won't be jumping up or down onto anything. So let's look at a specific example, one that I hope is familiar to you. This is, I'm not going to give the answers to the data that you've been given for this assessment, but I will give you an example. We will work through an example which is very similar. You've been given the same starting information, the mass, the acceleration of gravity, the resultant velocity, and the contact time. That's not the flight time, don't get those confused. And the angle of takeoff here is 45 degrees. The equations you will need to work out the jump distance are the three that we've just gone through and your trigonometry equations, I'm sorry to say. Okay, so what's the first thing we need to figure out then? What did we say a moment ago? It was the change in average vertical velocity. So we've been given the resultant velocity, that's 8.2 meters per second. We've got the angle of takeoff. So if we've got the angle and we've got the resultant velocity, we can use a bit of trigonometry to work out the vertical and the horizontal velocity. We just need to use our trig equations. Now, just take a moment, and you can pause here if you want, to label this triangle here. It's the exact same information that we have on here. I've just turned it into a triangle. Label the triangle, opposite, hypotenuse and adjacent, and think about which equation you are going to need to use to calculate the Vy, which I'll give you a hint will be the opposite side. Okay, so the hypotenuse is opposite the right angle. Haven't put that on here, but hopefully you appreciate that was in the bottom right hand corner. The opposite is here next to Vy, and the adjacent is next to Vx. And you are going to need the first of our equations, sine equals opposite over hypotenuse. So let's plug in what we know into our equation. We know that theta is 45, we know that the hypotenuse is 8.2, and we need to work out the opposite side, that's the vertical velocity. So we rearrange our equation. I've written, so sorry, I've done the sine of 45 here first. Forgot I did that, apologies. So if you just type in 45 into your calculator and hit sine, that will give you 0.7, round up to one decimal place here. So let's rearrange this equation. So we have 0.7 multiplied by 8.2, and this will give us 5.7 meters per second. So that is our vertical velocity. Now I won't go through the whole process, but you can pause here and try to work out Vx, okay, the adjacent side. You can either use trigonometry, or if you want, you can actually use Pythagoras' theorem. It's entirely up to you, but I'll pause here and you can work that out. Okay, you should have got 5.7 again, so 5.7 meters per second vertically and horizontally. And here is the same situation, just with the vertical and horizontal velocities labelled. So we now have all the information that we need. So the first thing we need to do is calculate the change in vertical velocity. So again, you can pause here and just work that out. Okay, you should have got minus 11.4 meters per second. And so from here then, we need to go on to do our next equation in order to work out the flight time. So you can ignore this. So the flight time is going to be delta t, where are we? Lost my equation there. Delta t equals the change in vertical velocity, which was minus 11.4 divided by the acceleration of gravity, which will give us 1.2. So in this case, our athlete, let's call him, was in the air for 1.2 seconds. We know the horizontal and vertical velocity, and now hopefully it's not too much of a stretch to calculate the jump distance. So here's our equation. I've left the arrow off just to make life easier for me. You've calculated the horizontal velocity, which we said was 5.7. You know the flight time now was 1.2, so you just need to multiply those numbers by each other, and you will be able to work out Dr. Devereux's jump distance, which was a staggering 6.8 meters. Very impressive. And that's it. I appreciate this is a very quick video, but it's if you can get trig trigonometry, you can do this. I actually think this is easier than trigonometry. It's just a bit unfamiliar. So just to recap, here's what you have to do, just to go through in stages. So we need to, hang on, I've not animated this very well. Here we go. First of all, you need to use your trigonometry to calculate the vertical velocity. Once you've done that, you need to calculate the average vertical velocity. After that, you can divide that value by minus 9.81 and you'll get the flight time. You can then do some trig in order to calculate the horizontal velocity, and then you take that horizontal velocity, multiply it by the flight time, and you will have the distance covered, and that is what you are going to want to present for your assessment. How far did that person jump? So I hope that has been helpful. I hope that makes sense, and if any of you have any questions, do feel free to drop me an email.